Welcome to Data Fundamentals Review. Today's world is full of data, but how do we define data? Data is unorganized information that is processed to make it meaningful. It can consist of facts, observations, or perceptions, numbers, characters, or symbols, images, or a mix of these. Data can be categorized by the level and rigidity of its structure. It can be structured, semi-structured, or unstructured. Structured data can be represented in rows and columns, just like a table. It has a well-defined schema and a rigid structure. These characteristics make relational databases, which store data in tables, ideal for structured data. Semi-structured data has some organizational properties, but not enough to be easily stored in the rows and columns required by a rigid tabular schema. Instead, semi-structured data is organized into a hierarchy using tags and metadata. Unstructured data does not have an identifiable structure. It does not follow any specific format, sequence, semantics, or rules. It cannot be organized into tabular format for storage in a relational database. Unstructured data is often stored in NoSQL databases. There is a multitude of data sources available today, from existing data stored in databases, flat files, or XML datasets, to data gathered from web scraping, data streams and feeds, to data collected from social platforms and Internet of Things devices with sensors. All of this data can be stored, processed, and made available for analysis, providing businesses with insights into their performance. Data can be held or transferred between systems in many different file formats. Common formats include delimited text files. In these files, the data is stored in rows, with each variable separated by a specific character, like a comma or a tab. Delimited files include comma-separated variable, or CSV, and tab-separated variable, or TSV files. Spreadsheets. In these files, the data is stored in rows and columns, just like a table. This makes the data easy to access and manipulate. You can use a spreadsheet to create CSV files. Language. Language files like extensible markup language, or XML, and JavaScript object notation, or JSON, have set rules and structures for encoding data to be sent over the internet. XML is readable by both humans and machines, is platform independent, and is programming language independent. That is, it can be read in any programming language. JSON is also programming language independent. It is a popular choice for sharing data of any size and type, including audio and video. It is returned by many APIs and web services. So, once you have gathered all your data, where should you store it? Structured and semi-structured data is often stored in databases, either relational databases like DB2 or non-relational databases like MongoDB. Each type of database is optimized for different types of operations. The type of data you need and the processes you want to apply to it will determine the type of storage you choose. An online transaction processing, or OLTP system, is optimized for storing the high volume of day-to-day operational data that many businesses rely on. OLTP systems are typically relational databases, but can also be built on relational databases. An online analytical processing, or OLAP system, is optimized for conducting complex data analytics. OLAP systems include relational and non-relational databases, data warehouses, data lakes, and other big data stores. Relational databases consist of structured data stored in related tables. The links between the tables are defined in a way that minimizes the duplication of data while still maintaining all the complex relationships required. Relational databases and their supporting systems are called Relational Database Management Systems, or RDBMS. Examples include IBM DB2, Microsoft SQL Server, Oracle, and MySQL. Relational databases are primarily OLTP systems, used to support day-to-day business activities such as customer transactions, human resource activities, and workflows. They can also be used to perform data analysis. For example, data from a customer relationship management system can be used to make sales projections. In this video, you learned that data is information like facts, observations, perceptions, numbers, characters, and images that can be processed to become meaningful. Data can be structured, semi-structured, or unstructured. Different data sources offer different types of data. For example, data from social media can be unstructured or semi-structured. Data can be stored in repositories like relational databases and non-relational databases, among many others. And data can be transferred in CSV, XML, and JSON files. Welcome to Information and Data Models. After watching this video, you will be able to describe the difference between an information model and a data model, explain the advantage of a relational model, and describe the difference between an entity and an attribute. This figure illustrates the relationship between an information model and a data model. An information model is an abstract, formal representation of entities that includes their properties, relationships, and the operations that can be performed on them. The entities being modeled can be from the real world, such as a library. Information models and data models are different and serve different purposes. An information model is at the conceptual level and defines relationships between objects. Data models are defined at a more concrete level, are specific, and include details. A data model is the blueprint of a database system. There are several different types of information models. The most familiar is the hierarchical, typically used to show organization charts. As shown in this figure, the hierarchical model organizes its data using a tree structure. The root of the tree is the parent node, followed by child nodes. A child node cannot have more than one parent. However, a parent can have many child nodes. The first hierarchical database management system was the Information Management System released by IBM in 1968 and was originally built as the database for the Apollo space program. The relational model is the most used database model for databases because this model allows for data independence. Data is stored in a simple data structure, tables. This provides logical data independence, physical data independence, and physical storage independence. An entity relationship data model, or ER data model, is an alternative to a relational data model. Using a simplified library database as an example, this figure shows an entity relationship diagram, or ERD, that represents entities, called tables, and their relationships. There are authors who write books, borrowers who take books out on loan, various copies of each book, etc. This is the final ER diagram, but how do we get there? An entity relationship model proposes thinking of a database as a collection of entities. Rather than being used as a model on its own, the ER model is used as a tool to design relational databases. In the ER model, entities are objects that exist independently of any other entities in the database. It is simple to convert an ER diagram into a collection of tables. The building blocks of an ER diagram are entities and attributes. Entities have attributes, which are the data elements that characterize the entity. Attributes tell us more about the entity. In an ER diagram, an entity is drawn as a rectangle and attributes are drawn as ovals. Entities can be a noun, person, place, or thing. Using a simplified library as an example, a book is an example of an entity. Attributes are certain properties or characteristics of an entity and tell us more about the entity. The entity, book, has attributes such as book title, the edition of the book, the year the book was written, etc. Attributes are connected to exactly one entity. The entity, book, becomes a table in the database, and the attributes become the columns in the table. Continuing the simplified library example, books are written by authors. Book is an entity, and author is an entity. For the entity author, the ER diagram would look like this. The entity, author, has attributes such as the author's last name, first name, email, city, country, and an author ID to uniquely identify the author. The entity author becomes a table in the database, and the attributes become the columns in the table. In the simplified library database, you progress through the process of identifying entities, such as borrowers who take books out on loan, various copies of each book, and copies of books out on loan. This is the final diagram. Each entity becomes a table in the database. In this video, you learned that information models are abstract, formal representations of entities that include their properties, relationships, and the operations that can be performed on them. Data models are defined at a more concrete level, are specific, and include details. The relational model is the most used data model for databases because this model allows for logical data independence, physical data independence, and physical storage independence. Entities are objects that exist independently of any other entities in the database. Entities can be a noun, a person, place, or thing, such as a book or an author. And attributes are the data elements that characterize the entity. For example, the book entity will have attributes like author and title. Welcome to Types of Relationships. After watching this video, you will be able to describe the building blocks of a relationship, explain the symbols used in a relationship set, and describe the difference between the one-to-one and many-to-many relationships. The building blocks of a relationship are entities, relationship sets, and crow's foot notations. Entity sets are represented by a rectangle. Relationship sets are represented by a diamond with lines connecting associated entities. Different techniques are used in representing relationships. For ease and understanding, this video uses the crow's foot notations. Some of these are the greater than symbol, the less than symbol, and a vertical line. An entity relationship diagram, or ER diagram, for the entity book would look like this. The entity, book, is drawn as a rectangle, and the attributes are drawn as ovals. Attributes are certain properties of that entity. For example, title, edition, year, price, etc. Attributes are connected to exactly one entity. For the entity author, the ER diagram would look like this. The entity author has attributes last name, first name, email, city, country, and author ID. Let us see how the entities book and author relate to each other. A book must be written by at least one author. However, a book can be written by two authors. It can also have many authors. As another example, one author can write just one book, two books, or multiple books. In both cases, there is a relationship between the book and the author. In these examples, you see that a book needs at least one author. The relationship set that comes here is authored by. One book must be written by one author. The thick lines indicate each entity in the entity set is involved in at least one and exactly one relationship. This is called a one-to-one relationship. Only entities are used in the relationship diagrams. Attributes are omitted because they can clutter the diagrams. Earlier, you saw that more than one author can write a book. This can be represented with a different notation called crow's foot notation. In this case, a less than symbol. This indicates that one book entity is participating in more than one relationship in the relationship set. This is called a one-to-many relationship. This could also be called a many-to-one relationship in that many authors write a single book. To represent many authors writing many books, use the greater than and less than symbols on either side of the relationship set. This is called a many-to-many relationship. Each entity in the entity set is participating in more than one relationship. Many books being written by many authors or many authors writing many books. In this video, you learned that the building blocks of a relationship are entities, relationship sets, and crow's foot notations. In a one-to-one relationship, one entity is associated with one and only one instance of another entity. For example, when one book has only one author. In a one-to-many relationship, one entity is associated with one or more instances of another entity. For example, when one book has many authors. And in a many-to-many relationship, many instances of an entity are associated with many instances of another entity. For example, when many authors write many different books. Welcome to Mapping Entities to Tables. After watching this video, you will be able to explain how an ER diagram translates into a relational database table with rows and columns. Entity relationship diagrams are the basic foundation for designing a database. In the relational database design, begin with an ER diagram, or ERD, and later map the ERD to the tables in a database. This example uses the ERD for the entity book. The entity, book, has several attributes. The entity and its attributes will be mapped to a table. For ease of understanding, let's separate the entity from the attributes. In this case, the entity book becomes a table with the same name, book. All the attributes translate into columns in the table. You will now see how a table would be represented in a relational database model. A table is a combination of rows and columns. While mapping, the entity becomes the table. And having said that, the table has not yet taken the form of rows and columns. The attributes get translated into columns in a table, providing the actual table form of rows and columns. Later, you can add some data values to each of the columns, which completes the table form. For the author example, the entity author becomes the table, and the attributes get translated to columns in the table, and adding data values into the columns completes the table. In this video, you learned that entity relationship diagrams, or ERD, are the basic foundation for designing a database. And to translate an ERD into a relational database table, the entity becomes the table, and the attributes become columns in the table. Welcome to Data Types. After watching this video, you will be able to explain what data types are, explain how data types are used in a database, identify some common data types, and describe the advantages of using appropriate data types. A database table represents a single entity, and the columns in the table represent attributes of that entity. For example, a table named Book could contain columns for title, published date, and the number of pages that they contain. The information entered into each column should always be of the same sort or type of data. In this example, the title column should contain textual data, the published date column should contain a date, and the pages column should contain a number. We can use this idea to define the type of data or data type that a column can store. The data type that you assign to a column controls the data that the column can store. For example, a text column can contain alphanumeric data, but a date column can only contain dates in a valid date format, and a numeric column can only contain numbers. Different database management systems may use different names for similar data types, but they generally support a standard set. So, let us look at the commonly used data types in an RDBMS. Character string data types include fixed-length data types and variable length. The length of a fixed-length character string is often denoted in brackets after the type name, such as car 10. This type uses the same amount of space in the database irrespective of the length of the actual data stored in it. For example, storing a city code such as NY for New York in a car10 column will still take up 10 characters of space. Variable length character strings, often named varchar, can specify a maximum length for the string. Numeric data types include integer types and decimal types. Integer data types only hold whole numbers with no decimal places. So 12 would be a valid entry, whereas 12.5 would not. Integer data types typically use 2 or 4 bytes of storage to hold at numbers from -2 million or 32,000 to +2 million or 32,000. Small ints enable you to use less space for smaller numbers, and big ints increase the size of the number that the data type can hold. Decimal data types can store whole numbers and decimal numbers. The sizes and precision of these data types vary between RDBMSs and have names such as numeric, decimal, dec, real, double, float, dec float, etc. Date/time data can be categorized into dates, times, and timestamps. Dates consist of 3-part values for the year, month, and day. And times also generally consist of a 3-part value for the hours, minutes, and seconds. A timestamp column is a combination of both and consists of 7 parts: year, month, day, hour, minute, second, and microsecond. Other commonly used data types include a Boolean, which only holds 1 bit of information, a 0 or a 1. You can use these for true, false, or yes/no type data. A binary string, which holds a sequence of bytes that represent image, voice, or other media data. A large object, or LOB, which is generally a very large object, such as a file. Often this type of data is stored outside of the main database table, and a pointer to it is held in the table. The XML data type can store platform-agnostic, unstructured data in a hierarchical form. In addition to the various built-in data types covered in this video, many relational databases also allow you to create your own custom or user-defined data types, UDTs, that are derived or extended from the built-in types. As you might have guessed, you can avoid using specific data types altogether and define every column to hold character data. However, using the appropriate data types provides many advantages. When you define the data type that a column should hold, you avoid incorrect data being inserted into that column. For example, if you try to add an author's name into the published date column of the books table, the insert will fail and you can take appropriate action. When date, time, and numeric data is correctly typed, you can accurately sort that data. For example, if you sort a character column containing numbers into ascending order, 102 may be listed before 12, or the query may fail. However, if the column is defined as numeric, you can be sure that the numbers will be returned in numerical order as generally expected. Similarly, you can accurately select ranges of data when it is correctly typed. For example, selecting all books published between January 1, 2001 and December 31, 2001. You can perform numeric calculations on typed data. For example, calculating the total cost of an order. And you can take advantage of standard functions such as returning the average of a column of ages or adding 2 days to an order date to estimate a shipping date. In this video, you learned that data types define the type of data that can be stored in a column. There are many different data types for all kinds of data, and using the correct data type for a column has many advantages. Welcome to Relational Model Concepts. After watching this video, you will be able to define relational terms such as relation, degree, and cardinality, and explain the difference between a relational schema and a relational instance. The relational model was first proposed in 1970 and is based on a mathematical model and mathematical terms. The building blocks of the relational model are relation and sets. The relational model of data is based on the concept of relation. A relation is a mathematical concept based on the idea of sets. A set is an unordered collection of distinct elements. It is a collection of items of the same type. It would have no order and no duplicates. A relational database is a set of relations. A relation is also the mathematical term for a table. A table is a combination of rows and columns. A relation is made up of two parts, relation schema and relation instance. A relation schema specifies the name of a relation, name and type of each of the columns, which are the attributes. The example here is the entity author. Author is the name of the relation. Author_ID is an attribute which can hold the data type char, which is a character string of a fixed length. Likewise, last name, first name, email, and city have the data type varchar, which is a character string of a variable length. The last attribute, country, also has a data type of char. This constitutes the relation schema. A relation instance is a table made up of rows and columns. The columns are the attributes, or fields. The rows are tuples. Degree refers to the number of attributes, or columns, in a relation. Cardinality refers to the number of tuples, or rows. In this example, the degree is 6 because there are 6 columns, and the cardinality is 5 because there are 5 tuples, or rows. In this video, you learned that relational model of data is based on the concept of relation. Relation is a mathematical term for table. And a relation schema specifies the name of a relation, while a relation instance is a table made up of the attributes, or columns, and tuples, or rows. Degree refers to the number of attributes, or columns, in a relation. Cardinality refers to the number of tuples, or rows, in a relation. Welcome to Database Architectures. After watching this video, you will be able to describe deployment topologies for databases and explain 2-tier and 3-tier architectures, including their layers such as database drivers, interfaces, and APIs. The deployment topology you use for your database is determined by how it will be used and accessed. For example, you can deploy a small database which requires limited user access on a local desktop. The database resides on the user's system and access is often limited to a single user. This deployment topology is sometimes known as single-tier architecture. It is useful for development and testing or when the database is embedded in a local application. You can deploy a larger database that many users must access in a client-server architecture. In this scenario, the database resides on a remote server, and users access it from client systems, often through a web page or local application. Some scenarios employ a middle tier, or an application server layer, between the application client and the remote database server. These client-server deployments are commonly used for multi-user scenarios and are typical for production environments. Deploying a database in the cloud is an increasingly popular option. In a cloud deployment, the database resides in a cloud environment and has all the advantages of a cloud-based service. You do not have to download or install the database software. You do not have to maintain the supporting infrastructure. And it is easy for users to access from wherever they are or whatever they are doing, so long as they have an internet connection. In cloud deployments, client apps and users typically access the database through an application server layer or interface in the cloud. Cloud deployments are very flexible. You can use them for development, testing, and full production environments. Let's look more closely at the client-server topology. It is also referred to as a 2-tier architecture. In a 2-tier database architecture, the database server and the application run in 2 separate tiers. The application in the client tier connects to the database server through some sort of database interface, such as an API or framework, which can be dependent on the programming language the application is written in. The database interface communicates with the database server through a database client or API that is installed on the client system. The Database Management System software, DBMS, on the server includes multiple layers, which on a high level can be categorized as Data Access Layer, Database Engine Layer, and Database Storage Layer. The Data Access Layer server includes interfaces for different types of clients, which can include data industry standard APIs such as JDBC and ODBC, command line processor or CLP interfaces, as well as vendor-specific or proprietary interfaces. The database server also contains an engine which compiles queries and retrieves and processes the data, then returns the result set. The database storage, or persistence layer, is where the data is stored, which may be on local storage on the same device, or reside physically on network storage or specialized storage appliances. In most production environments, especially in the last 20 to 25 years, the database server is typically not accessed directly, except by administrators. The client applications and users typically go through a middle tier, such as a web application server, a BI server, etc., and hence is referred to as three-tier architecture. In this architecture, the application presentation layer and the business logic layer reside in different tiers. The presentation layer is the interface with which end users interact, which could be a traditional desktop application, a web browser, or a mobile application. The client application communicates with an application server over the network. The application server encapsulates the application and business logic and communicates with the database server through a database API or driver. As an example, let's say the client application is an internet banking app or mobile phone. The app connects to a banking application server, which in turn connects with the bank's database servers where the user's account data is stored. In this video, you learned that databases are deployed in different topologies depending on which best suits the processing and access requirements. A single-tier topology is one where the database is installed on a user's local desktop. It is useful for small databases that only require single user access. In two-tier database topologies, the database resides on a remote server and users access it from client systems. In three-tier database topologies, the database resides on a remote server and users access it through an application server or a middle tier. And finally, in cloud deployments, the database resides in the cloud and users access it through an application server layer or another interface that also resides in the cloud. Welcome to Distributed Architectures. After watching this video, you will be able to describe shared disk distributed database architectures and their benefits. Describe replication and its benefits. Describe partitioning and sharding, and list the benefits of partitioning and sharding. So far, we have looked at architectures where the database resides on a single server. However, for critical or large-scale workloads where high availability and/or scalability is important, major RDBMSs also provide distributed architectures that utilize a cluster of machines to house the database. The main types of distributed database architectures include shared disk architecture and shared nothing architectures, which can employ either replication or partitioning. In some cases, you also find architectures that combine one or more of these techniques, or even specialized hardware components to achieve availability and scalability. In shared disk database architectures, multiple database servers process the workload in parallel, allowing the workload to be processed faster. Each database server is connected to shared storage infrastructure and to each other using high-speed interconnects. This allows the client workloads to be distributed amongst different database servers, allowing for scalability. In case of failure at one of the servers, the clients connected to it can be rerouted to other servers in the database cluster, achieving for high availability. Database replication is a technique whereby changes taking place on a database server are replicated to one or more database replicas. Client workload is distributed across servers for improved performance. When the replica is within the same location, it is known as a high availability replica. In case of a failure on the primary database server, such as a software or hardware failure, the clients connected to it can be rerouted to the HA replica. But what happens if there is a site-wide disaster? To mitigate against such scenarios, replicas can be set up in geographically distributed locations. So, in case the entire data center or location has an outage, such as a power outage, fire, earthquake, or flood, the clients can be routed to disaster recovery replicas. You can partition tables that need to contain very large quantities of data into multiple logical partitions, with each partition containing a subset of the overall data. For example, sales records for quarter 1, quarter 2, etc. When these partitions are placed on separate nodes in a cluster, it is called sharding. Each shard contains its compute resources, processing, memory, and storage to act on its subset or partition of data. When a client issues a query, it is processed in parallel on multiple nodes or shards of the database, and the query result from different nodes is synthesized and returned to the client. As the data or query workloads increases, additional shards and nodes can be added to the database cluster for increased parallel processing and improved performance. Database partitioning and sharding are more common for data warehousing and business intelligence workloads that involve very large volumes of data. In this video, you learned that in shared disk database architectures, multiple database servers process the workload in parallel, allowing the workload to be processed faster. In database replication, changes taking place on a database server are replicated to one or more database replicas. In a single location, database replication provides high availability. When a database replica is stored in a separate location, it provides a copy of the data for disaster recovery. In partitioning, very large tables are split across multiple logical partitions. And in sharding, each partition has its own compute resources. Welcome to Database Users and Usage Patterns. After watching this video, you will be able to recall the major categories of database users and their use cases for database access, as well as list the interfaces and tools used by different types of database users. How you access a database and the tools you use depends on your job role. Three main classes of database users are data engineers, data scientists and business analysts, and application developers. Data engineers and database administrators, or DBAs, generally access the database for administrative tasks such as creating and managing database objects, setting access controls, and monitoring and performance tuning. They typically use one or more of the following mechanisms for these tasks. GUI, or web-based management tools. Most databases come with graphical tools or web-based tools, especially for cloud databases or even mobile apps. In some cases, the tools provided by the database vendors may be limited in functionality or usability, so third-party tools or specialized tools may be available. Command line interfaces and utilities. With more fully functioning GUI tools, command line usage has declined, but a data engineer still requires some knowledge. Command line interfaces can be simple database commands you issue from the terminal. For example, db2 create database sample, mysql dump Sakila, sakila.sql, or interactive command line shells such as SQL Plus for Oracle or db2 CLP, db2, DB2 connect to sample, or SQL scripts and batch files that you execute from the shell. APIs. Many databases also include programmatic interfaces, or APIs, for administrative tasks that can be invoked from applications and tools that the data engineers or third parties create. Data analysts, data scientists, business analysts, and business intelligence analysts access databases for analyzing data in databases, deriving insight from this data, and making data-driven predictions. Therefore, their data access patterns involve accessing existing data sources and is typically read-only. However, at times they may need to create database objects and populate them with data, especially in their own sandbox environments. Some of the tools used for data science and machine learning include Jupyter, RStudio, Zeppelin, SAS, and SPSS. Popular tools for reporting, dashboarding, and business intelligence include spreadsheet software like Microsoft Excel, IBM Cognos, Microsoft Power BI, Tableau, and Microsoft Strategy. Both the DS and BI tools interface with relational databases using SQL interfaces and APIs. In many cases, these interfaces abstract away the need to use SQL directly. These users may, at times, also need to use SQL query tools for ad hoc querying. Most databases come with their own visual SQL query tools, but there are also third-party tools that work with a variety of databases. Application developers seldom access databases directly. They create applications which can require both read and write access to databases. Applications are written using programming languages such as C++, C#, Java, JavaScript, .NET, PHP, Perl, Python, and Ruby. These languages talk to the database using SQL interfaces and APIs such as ODBC and JDBC. Some databases, especially cloud-based ones, also include REST APIs for accessing data. And while it is possible to program your applications using these lower-level APIs or REST APIs, this is how applications in the past were developed. Most programmers these days use Object Relational Mapping, or ORM, frameworks for working with databases, as they are easier to use and mask the complexity of the underlying relational database and SQL. Examples of popular ORM frameworks include Active Record in Ruby applications, Django in Python, Entity Framework in .NET, Hibernate in Java, and Sequelize in JavaScript. In this video, you learned that three main classes of users are data engineers, data scientists and business analysts, and application developers. Databases can be accessed through graphical and web interfaces which make it easy to interact with the database visually. Command line tools and scripts can be cumbersome to use, but are powerful in the hands of an experienced data engineer and help with automating repetitive tasks. APIs and ORMs which help application developers create applications that access a database on behalf of a user or client application. Major categories of database applications include database management tools like PHP-MyAdmin or pgadmin, data science and BI tools like Microsoft Excel, IBM Cognos, and MicroStrategy, which enable data scientists and data analysts to analyze data and produce targeted reports. Purpose-built or off-the-shelf business applications for tasks such as e-commerce, supply chain, etc. And the method you choose to access the database depends on your needs. Welcome to Introduction to Relational Database Offerings. After watching this video, you will be able to summarize the history of relational databases, list popular commercial and open source databases, discuss the popularity of open source and commercial databases in the past decade, and discuss the rise in popularity of cloud databases. The first product recognizable as a relational database was in use during the 1960s, the IBM Sabre Seat Reservation System used by American Airlines. In the early 70s, Edgar F. Codd listed 12 rules to define relational databases. In the late 70s, Ingress, developed at the University of California, Berkeley, UCB, and System R, created at IBM San Jose, were in use. In 1976, Peter P. Chen proposed a new database model called Entity Relationship, or ER. The 1980s saw relational database systems become a commercial success. DB2 became the flagship database product for IBM, and Structured Query Language, or SQL, became the standard query language. In the late 80s, a workgroup in IBM designed a distributed relational database architecture enabling network-connected relational databases to cooperate to fulfill SQL requests. By the early 1990s, new client tools for application development, including Oracle Developer, Power Builder, and VB, along with tools for personal productivity like ODBC, Excel, and Access, were becoming popular. In the late 1990s, there was exponential growth of the database industry. Average desktop users began to use client-server database systems to access computer systems that contain legacy data. Some of the most popular relational databases included giants such as Oracle, Microsoft SQL Server, and IBM DB2. And in the 2000s, open-source DBs started to gain mainstream traction and started replacing many commercial databases. MySQL, PostgreSQL, and other systems brought open-source solutions to the Internet. The 2010s saw the popularity of cloud databases soar, with main players in the industry being Amazon RDS, IBM DB2 on Cloud, Microsoft SQL Server, and Oracle Cloud. For many years, the most popular relational database systems were those from large corporations which had the resources and talent to develop sophisticated, fully featured systems that supported the needs of industry at that time. These relational databases sold under commercial licenses and are still popular, with Oracle, Microsoft SQL Server, and IBM DB2 the market leaders. Most large corporations offer both on-premise and cloud-based versions of their products. In the late 2000s, open-source licensing for relational database systems like MySQL, PostgreSQL, and SQLite surged in popularity. Open-source databases operate under a variety of license types. Some examples of popular open-source databases are MySQL, produced by Oracle and offered under the General Public License version 2 license. PostgreSQL, produced by the PostgreSQL Global Development Group and offered under a PostgreSQL license, which is free and open-source permissive. And SQLite, produced by Dwayne Richard Hipp, and offered under a public domain license. The popularity of different kinds of database products is assessed monthly by industry analyst DB Engines. This list shows the 10 most popular relational database systems as of February 2021. Oracle, MySQL, Microsoft SQL Server, PostgreSQL, IBM DB2, SQLite, Microsoft Access, MariaDB, Hive, and Microsoft Azure SQL Database. This DB Engines ranking is based on mentions on websites, Google and Bing, general interest, Google Trends, frequency of technical discussions, Stack Overflow and DBA Stack Exchange, number of mentions in job offers, Indeed and Simply Hired, mentions in LinkedIn profiles, and other social media mentions. Over the past decade, there has been a dramatic change in the popularity of commercial versus open-source licensing across all types of software, including relational databases. The popularity of open-source relational databases has risen as the popularity of commercial databases has fallen. A 2021 DB Engine study found that open source systems account for 50.1% of the total DB Engine's popularity scores, up from 35.5% in 2013. A cloud database is a database service built and accessed through a cloud platform. It serves many of the same functions as a traditional database with the added flexibility of cloud computing. The popularity of cloud databases has increased steadily over the past decade. The trend is driven by organizations moving to the software as a service, or SaaS, model to take advantage of cloud benefits like increased scalability. Cloud databases are highly scalable, enabling organizations to process the vast amounts of data needed for data analytics. The popularity of cloud databases has more than doubled in the past decade, and this growth is set to continue. According to Gartner, by 2022, 75% of all databases will be deployed or migrated to a cloud platform. Leading cloud databases include Amazon DynamoDB, Microsoft Azure Cosmos DB, Microsoft Azure SQL DB, Google BigQuery, and Amazon Redshift. In this video, you learned that relational databases are available with commercial licenses from companies like IBM, Oracle, and Microsoft. Open source relational databases are offered with a variety of licenses that make them free to the user. The popularity of open source relational databases has risen to approximately 50% in the past decade. And the popularity of cloud databases has more than doubled in the past decade. Welcome to DB2. After watching this video, you will be able to describe DB2, its histories and features, list various DB2 products and deployment options, describe DB2 on cloud and its plans, explain how you can work with DB2 on cloud, describe DB2 high availability options, and describe DB2 scalability with partitioning. Database 2, or DB2, was first released by IBM in 1983 and was an early example of a relational database management system. This first release ran on IBM mainframe computers, but over the years, different versions were developed to run on many other platforms, including OS/2, Unix, Linux, and Windows. After some time, the product was rewritten to use the same codebase across the multiple operating systems so that you can easily port applications accessing DB2 data from one operating system to another. After many iterations of the offering across many platforms and with enhanced functionality, today DB2 is a whole suite of database management products, including DB2 Database, DB2 Warehouse, DB2 on Cloud, DB2 Warehouse on Cloud, DB2 Big SQL, DB2 Event Store, and DB2 for z/OS. There are many ways to evaluate these products. You can use DB2 Database Community License for free with a 100 GB data limit, or you can download a free Docker image of DB2 Database. You can also use the free Lite plan of DB2 on Cloud for development and evaluation purposes on IBM Cloud. DB2 Warehouse Enterprise Edition and DB2 Big SQL are available in no-cost trial editions. You can use DB2 Warehouse on Cloud for free up to 1 GB of data. And you can download a free version of DB2 Event Store Developer Edition. The DB2 products all use AI-powered functionality to simplify the management and querying of your data, both on-premises and in cloud environments. You can use machine learning algorithms to improve the efficiency and performance of queries. The Column Store feature to improve performance and reduce overheads for analytic workloads by directing queries to specific columns rather than processing an entire data table. And the data skipping feature to reduce overheads by automatically avoiding processing data that is not required in a particular query. The common SQL engine across all the DB2 family means that you can write a query once and be sure it will work with other products in the family. This simplifies migration of applications between products and platforms. The support for all data types, relational, structured, and unstructured, means you can access all of your corporate data to make better business decisions. And the DB2 replication functionality enables you to implement high availability and disaster recovery solutions. DB2 provides scalability in a number of ways. For short peaks, you can extend on-premises storage and power levels onto hosted cloud deployments, and you can independently scale power and storage in a managed cloud deployment to only use and pay for extra resources when you need them. Or in DB2 Warehouse, you can use the database partitioning feature to transparently split data across partitions and servers to maximize the compute power available and enable massively parallel processing. The DB2 family provides you with a range of data management products to work with data on-premises or in the cloud. DB2 Database is a powerful enterprise-ready on-premises RDBMS optimized for OLTP. It is supported on Linux, Unix, and Windows, and provides performance, high availability, scalability, and resilience. DB2 Warehouse is an on-premises data warehouse that provides advanced data analytics, massively parallel processing, and machine learning. DB2 on Cloud is a fully managed cloud-based SQL database which provides similar features to DB2 Database: performance, high availability, scalability, and resilience. And DB2 Warehouse on Cloud is a fully managed, elastic, cloud-based data warehouse that provides similar features to the on-premises DB2 Warehouse. You can deploy both of the cloud-based products on IBM Cloud and Amazon Web Services. DB2 Big SQL is an SQL on Hadoop engine that provides massively parallel processing and advanced querying functionality. You can use it to query a range of data sources, including Hadoop HDFS and Web HDFS, RDBMS, NoSQL, and other object stores. You can integrate it with Cloudera Data Platform or use a service on IBM Cloud Pak for data. And DB2 Event Store is a memory-optimized database that you can use to ingest and analyze streamed data for event-driven applications. It includes IBM Watson Studio, which provides you with a development environment for machine learning models. And finally, DB2 for ZOS, an enterprise data server for IBM Z. It provides a mission-critical data solution with integration for analytics, mobile, and cloud that supports thousands of customers and millions of users. Cloud Pak for Data is a fully integrated data and AI platform that you can use to work with and manage all of your data. It runs on Red Hat OpenShift in a container, so you can deploy it on any private, public, or hybrid cloud. Using Cloud Pak for Data, you can connect to DB2 or any other data source wherever it may be stored. Use the Watson Knowledge Catalog to organize your data. Work with a range of analytics services to gain insight on your data. And use Watson and other services to infuse AI into your systems. DB2 on Cloud is a great way to get started with DB2. It offers 3 plans for you: Light, Standard, and Enterprise. The Light plan is free and time unlimited, meaning that you can use it in your projects without worrying about a time-limited trial period coming to an end. The plan is limited to 200 megabytes of data and 15 simultaneous connections. The Standard plan provides flexible scaling of compute capability and storage, as well as built-in 3-node high-availability clustering. And the Enterprise plan provides you with a dedicated database instance, again with flexible scaling of compute capability and storage and built-in 3-node high-availability clustering. You can deploy DB2 on cloud on the IBM Cloud Platform or on Amazon Web Services. Once running, you can access your DB2 on Cloud databases by using the CLP Plus command line interface. The the DB2 on Cloud GUI console, or standard APIs such as ODBC, JDBC, and REST. You can also easily load data from Excel, CSV, and text files from Amazon S3 Object Storage using the GUI console, and you can programmatically load data from IBM Cloud Object Storage. DB2 provides high availability disaster recovery, or HADR functionality to support high availability systems. HADR replicates changes made at a primary database to multiple standby servers. If the primary database fails for any reason, hardware, software, or network issues, you can automatically promote one of the standby databases to be the primary database, redirect client applications to this new primary database, and continue to replicate to the other standby servers in the group. When the original primary database comes back online, it can either take the place of a standby server or be promoted back to the primary position. DB2 Warehouse offers massively parallel processing and data analytics for BI workloads. At times, you may need to scale the storage capabilities of your system to meet peak demand or to reduce costs when demand is low. Data in DB2 Warehouse is stored in data nodes. To scale up your storage capacity, you just need to add a node to your deployment. The partitions and their workloads are then automatically rebalanced across the new node setup. Similarly, to scale down, you just remove a node to return to your original state. In this video, you learned that DB2 is a family of products that you can use to work with and manage your data in whatever way you need. You can deploy DB2 across many platforms, both on-premises and in the cloud. Cloud Pak for Data includes DB2 and many IBM tools for data. DB2 on Cloud is a fully managed cloud-based SQL database that can run on IBM Cloud or AWS. And DB2 provides high availability, disaster recovery, and scalability functionality. Welcome to MySQL. After watching this video, you will be able to describe MySQL, explain how you can work with MySQL, list some of the MySQL storage engines, and understand MySQL high availability and scalability options. MySQL was first developed by a Swedish company, MySQL AB, and named after Mai, the daughter of one of the co-founders of MySQL AB, Monty Widenius. The company was later acquired by Sun Microsystems, which in turn was acquired by Oracle Corporation. The dolphin in the MySQL logo is named Sakila, which was chosen from a list of suggestions made in a Name the Dolphin contest. MySQL soared in popularity in the late 1990s and early 2000s, partly because it was a key component in the LAMP, Linux operating system, Apache web server, MySQL database, and PHP scripting language stack, which was being used to build many popular websites at the time. MySQL is available under dual license, the open source GNU GPL, and a commercial license for applications and solutions that embed MySQL. Because the GNU GPL is open source, there have been various forks of MySQL, the most prominent being MariaDB, which is led by some of the original developers of MySQL. MySQL is an object relational database management system. It is a popular low-maintenance database and is available in various flavors and editions, including a clustered version for demanding workloads. You can run MySQL on many versions of Unix as well as Microsoft Windows and Linux, and you can write client applications for it using most modern programming languages. MySQL uses standard SQL syntax, as well as its own extensions for additional functionality, such as the load data statement that very quickly reads rows from a text file into a database table. MySQL works primarily with relational data, but also supports JSON. Like many other RDBMS, MySQL supports multiple storage engines. The storage engine is the component that handles the SQL operations on a table and defines what features that table can use. So, you base your choice of engine for a particular table on the expected workload and needs of that table. For example, the default MySQL storage engine is InnoDB, which supports transactions to ensure the consistency of your data, row-level locking to improve multi-user performance, clustered indexes on primary keys to increase the performance of regularly executed queries, and foreign key constraints to maintain data integrity. This engine provides a balance of high performance and reliability. MySQL also supports the MyISAM engine, which is good for workloads with mainly read operations and few updates, such as data warehouse or web applications. It uses table-level locking, which inhibits performance in a read-write environment. Another commonly used engine is the NDB engine, which supports multiple instances of MySQL servers running in a cluster. This is primarily used for applications that require high levels of availability and redundancy. MySQL supports high availability and scalability. You can use replication to create a copy of your data on one or more replicas. Data changes at the source database are then also performed at the replicas. Multiple copies of the same data means that you can share the read load for your data across the replica set, improving scalability. And replication also increases availability, because if the source database fails, you can fail over to use one of the replicas instead. MySQL provides two clustering options. The first uses the InnoDB storage engine with group replication and enables you to work with one read-write primary server and multiple secondary servers. You can then use MySQL Router to load balance client applications across the multiple server instances. And in the event of unplanned downtime of any of the servers, MySQL Router will reconnect client applications to an available server. Alternatively, the MySQL Cluster Edition uses the NDB storage engine to provide a highly available and scalable solution. Multiple MySQL server nodes access a set of data nodes, usually stored in memory. Running multiple data nodes provides redundancy and hence increased availability in the event of failure. And running multiple server nodes provides for scalability. In this video, you learned that MySQL is an object relational database available in various editions, supports many operating systems, supports a range of languages for client application development, supports relational and JSON data, provides multiple storage engines for differing workloads, and provides high availability and scalability options. Welcome to PostgreSQL. After watching this video, you will be able to describe PostgreSQL, explain how you can work with PostgreSQL, and describe replication functionality in PostgreSQL. PostgreSQL originates from the Postgres project at the University of California more than 30 years ago. Postgres was used for many research and production applications across a range of industries, including financial services, aviation, and medicine. In 1994, the open-source Postgres 95 was released, which included an SQL language interpreter. This was soon renamed PostgreSQL and is today generally pronounced as simply Postgres. You can use it as part of the LAPP, Linux, Apache, PostgreSQL, and PHP stack for web applications and websites. And you can also use independently developed extensions for additional functionality, such as PostGIS for geographic and spatial data handling. PostgreSQL is a free, open-source, object relational database management system. The open source part means that you can use, modify, and distribute the Postgres source code to meet your business requirements. The object part describes that, like object-oriented programming languages, it supports inheritance and overloading. You can use these techniques to simplify your design and reuse database objects. Postgres is compatible with most of today's commonly used operating systems, and its low maintenance threshold make it easy to implement in an organization. It supports many programming languages, enabling you to integrate it with your web applications, and supports ANSI SQL standards. When using Postgres, you can use all the standard relational database constructs, such as keys, transactions, views, functions, and stored procedures. And you can also use some of the NoSQL functionality, such as JSON for structured data and HStore for non-hierarchical data. Postgres supports replication for high availability. It supports two-node synchronous replication. This stores a copy of your data on a second server and applies each change you make to Node 1 at Node 2. You can then share read loads across the two servers, and if Node 1 fails, you can enable Node 2 to service all clients until Node 1 is running again. It also supports multi-node asynchronous replication for high availability and scalability. Here, one master node distributes its changes to multiple read-only replicas for scalability purposes. And again, if the read-write node fails, you can quickly replace it with one of the read-only replicas. For even greater flexibility for scaling applications, you can use commercial editions such as EDB PostgreSQL Replication Server, which provide multi-master read-write replication. This enables you to run multiple read-write databases that all replicate changes with each other. If one fails, users can easily be redirected to another instance until it is available again. Other technologies that have been added to PostgreSQL in recent releases to enhance scalability and working with larger datasets include partitioning, which enables you to split a large table into multiple smaller sections, or partitions to improve query performance, and sharding, which enables you to store horizontal partitions across multiple remote servers. In this video, you learned that PostgreSQL is an open-source object relational database. It supports a range of languages for client application development. It supports relational, structured, and non-structured data. And it supports replication and partitioning for high availability and scalability. Welcome to Types of SQL Statements. At the end of this video, you will be able to distinguish between data definition language statements and data manipulation language statements. SQL statements are used for interacting with entities, that is, tables, attributes, that is, columns, and their tuples, or rows with data values, in relational databases. SQL statements fall into two different categories: data definition language statements and data manipulation language statements. Data definition language, or DDL statements, are used to define, change, or drop database objects such as tables. Common DDL statement types include create, alter, truncate, and drop. Create, which is used for creating tables and defining its columns. Alter is used for altering tables, including adding and dropping columns and modifying their data types. Truncate is used for deleting data in a table, but not the table itself. Drop is used for deleting tables. Data manipulation language, or DML statements, are used to read and modify data in tables. These are also sometimes referred to as CRUD operations, that is, create, read, update, and delete rows in a table. Common DML statement types include insert, select, update, and delete. Insert is used for inserting a row or several rows of data into a table. Select reads or selects row or rows from a table. Update edits row or rows in a table, and delete removes a row or rows of data from a table. Now you know that DDL or data definition language statements are used for defining or changing objects in a database, such as tables. And DML or data manipulation language statements are used for manipulating or working with data in tables. Thanks for watching this video. Welcome to Creating Tables. After watching this video, you will be able to list considerations for creating tables, describe how to create a table in a graphical interface like DB2 on Cloud, and explain how to alter table structure after creation. When creating a table, you will need some information at hand. First, where will you create the table? Many relational databases have schemas, which provide a way of organizing database objects into logical groups. For example, in IBM DB2 on Cloud, you will store tables, views, functions, and other database objects in your own user schema. Next, you must ensure you have all the information you need to create the table, including a name for the table and names and data types for each column. You should also consider whether a column can contain duplicate values or if a column will allow null values. Use the entity relationship diagram you created as part of your database design to guide you. You can create tables in several different ways. Most databases have a visual or graphical interface that you can use to create and modify tables. These are great for small occasional tasks, but they don't scale well. You can also create tables with the Create Table SQL statement, which can be included in a script file to help you automate the creation process when you are creating multiple tables. Finally, some databases have administrative APIs for creating and managing databases programmatically. The illustrations provided in this video are based on DB2 on Cloud console examples. Similar concepts apply to other databases. The first step in creating a table using the DB2 on Cloud console is to choose a schema to hold the table. In this case, the user schema CQC63405 is selected. In DB2, the default schema is the username. In this example, you can see that the username is CQC63405. Each user will have a different username, so you will see a different username in your own DB2 database. You can create new schemas to hold your tables, views, and other database objects. In this case, the user schema CQC63405 is selected. Select New Table to create a new table. Give your new table a name. In this example, the table is named Employee Details. Because it exists within the CQC63405 schema, the fully qualified name for this table is CQC63405.EmployeeDetails. The new table has a single column by default. You can rename this column to fit your needs. Set a data type for your column by selecting one from the list. Use Add Column to continue to add columns until you have constructed the entire table. Remember to specify the data type for each column. You can also specify whether the column accepts null values and specify length and scale depending on the data type. Lastly, click Create. There are many actions you can take once you have created the table. You can drop or delete the table. You can generate SQL code to perform actions such as select, insert, update, and delete. You can alter the table to add a new column, set constraints, or change the structure of the table in some other way. And you can see the database objects that the table depends on. In this video, you learned that many relational database management systems, RDBMS, have schemas which contain tables, views, functions, and other database objects. Most RDBMS provide a GUI which you can create tables through. You can also use SQL statements to create tables. And you can alter the structure of the table after it's created, should you need to add a column, change a data type, or add a primary or foreign key. Welcome to Create Table Statement. At the end of this video, you will be able to explain how the entity name and attributes are used to create a relational database table. Now let's look at the most common DDL statement, create. The syntax of the create table is shown here. You start with create table, followed by the name of the table you want to create. Then enclose the rest of the statement inside a pair of parentheses or round brackets. Each row inside the parentheses specifies the name of a column, followed by its data type and possibly some additional optional values that we will see later. Each attribute or column definition is separated by a comma. For example, if we want to create a table for provinces in Canada, you would specify create table provinces, open parentheses, ID car, 2, primary key, not null, comma, name varchar, 24, close parentheses. In this example, the data types used are car, which is a character string of a fixed length, in this case 2, and varchar, which is a character string of a variable length. In this case, the variable character field can be up to 24 characters long. Issuing this statement would create a table in the database with 2 columns. The first column, ID, for storing the abbreviated 2-letter province shortcodes such as AB, BC, etc. And the second column, called name, for storing the full name of the province such as Alberta, British Columbia, etc. Now let's look at a more elaborate example based on the library database. This database includes several entities such as author, book, borrower, etc. Let's start by creating the table for the author entity. The name of the table will be author, and its attributes such as author_ID, first name, last name, etc. will be the columns of the table. In this table, we will also assign the author_ID attribute as the primary key, so that no duplicate values can exist. Recall, the primary key of a relational table uniquely identifies each tuple or row in a table. To create the author table, issue the following command. Create table author, open parentheses, author_ID, car2, primary key not null, comma, last name varchar 15, not null, comma, first name varchar 15, not null, comma, email varchar 40, comma, city varchar 15, comma, country car 2, close parentheses. Note that the author_ID is the primary key. This constraint prevents duplicate values in the table. Also note that the last name and first name have the constraint not null. This ensures that these fields cannot contain a null value, since an author must have a name. Now you know that create is a DDL statement for creating entities or tables in a database. And the create table statement includes definition of attributes of columns in the table, including names of columns, data types of columns, and other optional values if required, such as the primary key constraint. Thanks for watching this video. Hello and welcome to Alter, Drop, and Truncate tables. After watching this video, you will be able to describe the alter table, drop table, and truncate statements, explain the syntax, and use the statements in queries. You use the alter table statement to add or remove columns from a table, to modify the data type of columns, to add or remove keys, and to add or remove constraints. The syntax of the alter table statement is shown here. You start with alter table, followed by the name of the table that you want to alter. Differently to the create table statement, though, you do not use parentheses to enclose the parameters for the alter table statement. Each row in the alter table statement specifies one change that you want to make to the table. For example, to add a telephone number column to the author table in the library database to store the author's telephone number, use the following statement. Alter table author, add column, telephone underscore number, big int, semicolon. In this example, the data type for the column is big int, which can hold a number up to 19 digits long. You can also use the alter table statement to modify the data type of a column. To do this, use the alter column clause specifying the new data type for the column. For example, using a numeric data type for telephone number means that you cannot include parentheses, plus signs, or dashes as part of the number. You can change the column to use the car data type to overcome this. This code shows how to alter the author table. Alter table author, alter column telephone underscore number, set data type car, open parentheses, 20, close parentheses, semicolon. Altering the data type of a column containing existing data can cause problems, though, if the existing data is not compatible with the new data type. For example, changing a column from the car data type to a numeric data type will not work if the column already contains non-numeric data. If you try to do this, you will see an error message in the notification log and the statement will not run. If your spec changes and you no longer need this extra column, you can again use the alter table statement, this time with the drop column clause to remove the column as shown. Alter table author drop column telephone underscore number semicolon. Similar to using drop column to delete a column from a table, you use the drop table statement to delete a table from a database. If you delete a table that contains data, by default the data will be deleted alongside the table. The syntax for the drop table statement is drop table, table underscore name, semicolon. So you use this statement, drop table author, semicolon, to remove the table from the database. Sometimes you might want to just delete the data in a table rather than deleting the table itself. While you can use the delete statement without a where clause to do this, it is generally quicker and more efficient to truncate the table instead. You use the truncate table statement to delete all of the rows in a table. The syntax of this statement is truncate table, table underscore name, immediate, semicolon. The immediate specifies to process the statement immediately and that it cannot be undone. So, to truncate the author table, you use this statement, truncate table author immediate, semicolon. In this video, you learned that the alter table statement changes the structure of an existing table, for example, to add, modify, or drop columns. The drop table statement deletes an existing table. And the truncate table statement deletes all rows of data in a table. Welcome to Data Movement Tools and Utilities. After watching this video, you will be able to indicate scenarios that necessitate data movement. List various tools and utilities used for data movement in relational databases. Explain the purpose of backup and restore utilities to move data into and out of a database. Describe import and export utilities and how they differ from backup and restore. Recall how to export a table to a CSV file. Explain the benefit of load utility and how it differs from import. And indicate when to use which data movement tool or utility. Data engineers and database administrators will often need to move data into and out of an existing database. This could be for several reasons, such as initially populating the entire database and all objects with it, such as tables, creating a working copy of the database for development and testing purposes, creating a snapshot of the state of the database at a particular instance in time for the purposes of disaster recovery, creating a new table or a set of tables from data that has been extracted from external data sources or files, and adding or appending data into one or more existing tables. Most databases support many different ways to move data in and out of the database using multiple file formats. Each database has its own tools and utilities for data movement, but they can be broadly classified into three categories: backup and restore, import and export, and load. Let us look at each of these. One method for moving data between databases is to perform a backup and restore. The backup operation creates a file or a set of files that encapsulates all the database objects and their data. The restore operation creates an exact copy of the original database from the backup files. Backup and restore operations preserve all objects in the database, including schemas, tables, views, user-defined data types, functions, stored procedures, table constraints, triggers, security settings, relationship between objects, and of course, the data in all tables. Backups are often taken on a periodic basis to preserve copies of a production database for disaster recovery purposes. Backup and restore operations can also be performed for creating additional copies of the database for development and test purposes. The import operation reads data from a file and performs a series of insert statements against the target table. The export operation selects data from the specified table and saves it into a target file. Depending on the database, import and export operations can be performed using multiple interfaces. Most databases provide at least a command line utility. Management APIs for some databases include support for import and export. In some cases, the graphical or web administration tools include a visual interface for these operations. And there is also third-party tools that allow these operations to be performed with many different DBMSs. Most databases support multiple file formats for importing and exporting data. The most commonly used formats are DEL, or Delimited ASCII 2, for data exchange among a wide variety of database managers and file managers. This common approach to storing data uses special character delimiters to separate column values. A well-known example is comma-separated variable, or CSV files. ASC, or Non-Delimited ASCII 2, for importing or loading data from other applications that create flat text files with aligned column data. PCIXF, PC version of the Integration Exchange Format, or IXF. PCIXF is a structured description of a database table that contains an external representation of the internal table. JSON. With the popularity of JSON and REST web services, some databases and third-party tools have also started to support importing and exporting data to and from JSON files. Let's look at some examples of performing import and export operations from different interfaces. In DB2, the command line import and export utilities allow you to type the file names, file formats, table names, and optionally, message files for importing and exporting data. Note that the export utility in DB2 allows you to specify an SQL query, allowing you to export just a subset of the data in a specified table if needed. As an example of a simple export, let's look at how to export a table to a CSV file in the DB2 console. In your schema, select the table you want to export. Select the table and then click View Data. Select the Export button. Click Export to CSV. You can specify a name and location to save the CSV file. As an alternative to the import utility, some databases provide load utilities. The load utility is faster than the import utility because it writes formatted pages directly into the database, while the import utility performs a series of SQL insert statements. However, it does not perform referential or table constraints checking, so you may prefer to use the import utility if you need those extra checks. The load utilities may also bypass database logging, which also helps with higher performance. While import may work well for smaller tables, when it comes to very large volumes of data, the load utilities are preferred. You can activate the DB2 import utility from the command line or by calling its API through an application, or even using visual database management tools. In this video, you learned that data movement is required for initially populating databases and tables, adding or appending data, and making copies for development tests or disaster recovery. Backup and restore utilities are used to create and recover copies of entire databases, including all objects like tables, views, constraints, and their data. Import utility enables inserting data into a specific table from different formats such as DEL, CSV, ASCII, and IXF. Export utility enables saving data from a specific table into various formats like CSV. And load utilities enable high-performance insertion of data into specified tables and is useful for large volumes. Welcome to Loading Data. After watching this video, you will be able to explain when to use load data functionality, list the types of data source you can load data from, and describe the 4 steps in the load data process in the DB2 web console. Using SQL statements such as insert to add data into tables can work well for a few rows or when you are developing and testing your database systems. However, it is often not practical to use this method to load hundreds or thousands of rows of data. The process of inputting the data for each row and then uploading it to the database is not very efficient. Instead, most relational database management systems, or RDBMS, provide a method of directly loading large amounts of data into tables in a quick, efficient, and scalable manner. Your data might originate from a range of different sources in a variety of formats. For example, you might want to populate your table with information exported from another database in delimited text files, or object data output from a bespoke application. In the DB2 web console, you can use the Load Data utility to load data stored in delimited text files on your local computer. In S3 Object Storage, that is, the storage service from Amazon Web Services, or in Cloud Object Storage, that is, the cloud storage service from IBM. So let us take a look at an example of how to load data into a table from a CSV file using the DB2 web console. To begin loading data in the web console, open the 3-bar menu and in the Load section, click Load Data. You then follow a series of 4 steps to define how to load your source data into your target tables. First, identify the type and location of your source data. Then select the target for the data. Next, define any configurable aspects of the data. And then finally confirm everything before starting the load process. On the source page, select the location of the existing data and enter any authentication information which that storage type requires. For example, for data in IBM Cloud Object Storage, you provide the COS authentication endpoint, access key, and secret access key. Whereas for a locally stored CSV file, you simply identify the file to upload. On the target page, select the target schema and table for the data location. You can also specify here whether to append the new data to the end of the table or overwrite the existing data with the new data. Note that if you use the overwrite option, even if your load fails, you will still lose all of the existing data in that table. Alternatively, you can click New Table to load the data into an entirely new table, using the format of the new data to define the data types for the columns. On the Define page, you define the character encoding and delimiter for the text file, whether there are column headings in the first row, and what time and date formats to use. And on the Finalize page, you can review all of the settings before beginning to load the data. When the load completes, the console displays the status of the process and also shows any errors or warnings that the load process has raised. In this video, you learned that loading data is quicker, more efficient, and more scalable than using multiple insert statements. You can load data from a variety of data sources, including delimited text files and cloud object storage. And the Load Data utility is a simple-to-use interface in the DB2 web console. Welcome to Database Objects and Hierarchy. After watching this video, you will be able to recall the hierarchy of database objects. Describe an instance of a database. Define the term relational database. Explain when to create a new database. Define the term schema. Compare user schemas and system schemas. Describe a database partition. And list commonly used database objects. Relational Database Management Systems, or RDBMSs, contain many objects that database engineers and database administrators must organize. Storing tables, constraints, indexes, and other database objects in a hierarchical structure allows database administrators to manage security, maintenance, and accessibility. This example hierarchy gives you an overview of how RDBMSs are structured, although slight variations may occur between products. Most RDBMSs begin with an instance, a single way of organizing the database and everything it contains. Many RDBMSs permit more than one database within a single instance. You will generally find at least one schema at some level in the hierarchy. A schema is a logical grouping of objects within a database. Schemas define how database objects are named and prevent ambiguous references. Some RDBMSs consider the schema a parent object of a database, and others consider it a database object. Within a schema are the database objects, including tables, constraints, and indexes. An instance is a logical boundary for a database, or set of databases, where you organize database objects and set configuration parameters. Every database within an instance is assigned a unique name, has its own set of system catalog tables, which keep track of the objects within the database, and has its own configuration files. You can create more than one instance on the same physical server, providing a unique database server environment for each instance. The databases and other objects within one instance are isolated from those in any other instance. You can use multiple instances when you want to use one instance for a development environment and another instance for a production environment, restrict access to sensitive information, or control high-level administrative access. Not all RDBMSs use the concept of instances, often managing database configuration information in a special database instead. In cloud-based RDBMSs, the term instance means a specific running copy of a service. A relational database is a set of objects used to store, manage, and access data. These objects include tables, views, indexes, functions, triggers, and packages. Database objects can be either defined by the system, built-in objects, or defined by the user, user-defined objects. In a relational database, database engineers establish relationships between tables to reduce redundant data and improve data integrity. A distributed relational database shares tables and other objects across different but interconnected computer systems. A schema is a specialized database object that provides a way to group other database objects logically. A schema can contain tables, views, nicknames, triggers, functions, packages, and other objects. When you create a database object, you can assign it to a schema. If you want to assign the object to a specific schema, you can explicitly include the schema name. If you don't include the schema name, the object is implicitly assigned to the current schema. In most RDBMSs, the default schema is the user schema for the currently logged on user. A schema also provides a naming context. Using the schema name as a name qualifier enables you to distinguish between objects with the same name in different schemas. For example, the schema names internal and external make it easy to distinguish two different sales tables, internal.sales in the internal schema and external.sales in the external schema. Thus, schemas enable multiple applications to store data in a single database without encountering namespace conflicts. Many RDBMSs use a specialized schema to hold configuration information and metadata about a particular database. For example, tables in a system schema can store lists of database users and their access permissions, information about the indexes on tables, details of any database partitions that exist, and user-defined data types. A partitioned relational database is a relational database whose data is managed across multiple database partitions. You can partition tables that need to contain very large quantities of data into multiple logical partitions, with each partition containing a subset of the overall data. Database partitioning is used in scenarios that involve very large volumes of data, such as data warehousing and data analysis for business intelligence. Database objects are the items that exist within the database. The process of database design includes defining database objects and their relationships with each other. In most RDBMSs, you can create objects such as tables, logical structures consisting of rows and columns which store data. Constraints. Within any business, data is often subject to certain restrictions or rules. For example, an employee number must be unique. Constraints provide a way to enforce such rules. Indexes. An index is a set of pointers used to improve performance and ensure the uniqueness of the data. Views. A view provides a different way of representing the data in one or more tables. A view is not an actual table and requires no permanent storage. And aliases. An alias is an alternative name for an object, such as a table. It can be used to provide a shorter, simpler name to reference an object. You can create and manage database objects through graphical database management tools, scripting, or accessing the database through an API. If you are using SQL to create or manage the object, you will use data definition language statements like create or alter. In this video, you learned that an instance is a logical boundary for a database or set of databases where you organize database objects and set configuration parameters. A relational database is a set of objects used to store, manage, and access data. Relationships between tables reduce redundant data and improve data integrity. A schema is a specialized database object that provides a way to logically group tables, views, nicknames, triggers, functions, packages, and other database objects. Schemas provide naming contexts so you can distinguish between objects with the same name. User schemas contain database objects, like tables, views, and functions. System schemas contain configuration information and metadata for the database. You can split very large tables across multiple partitions to improve performance. And database objects are the items that exist within the database, such as tables, constraints, indexes, views, and aliases. Welcome to Primary Keys and Foreign Keys. After watching this video, you will be able to describe primary and foreign keys and create primary and foreign keys. You can use a primary key to uniquely identify every row in a table. In some tables, the choice of primary key is easy because it is a naturally occurring unique attribute of entity. For example, the book ID of a book or the employee ID number of a staff member. If your table does not have an existing unique attribute, you can add a column to the table to serve as the primary key. Or if a combination of two attributes uniquely identifies each row, you can create a primary key across the two columns. For example, where employees have a unique identifier within their work site, you can use the combination of their site ID and employee ID. Note that each table can only have one primary key. You can create a primary key when you create the table by using the primary key clause of the Create Table statement. In the parenthesis for the primary key clause, state the name of the column or columns that will be the primary key. Alternatively, you can create a primary key on an existing table by adding the Add Primary Key clause of the alter table statement. And again, in the parenthesis, state the name of the column or columns that will be the primary key. You use primary and foreign keys to define the relationships between your tables. A foreign key is a column in a table which contains the same information as the primary key in another table. For example, the copy table might list all the books that the library owns. Therefore, the book_ID of a copy of an individual book must exist in the book table as a valid book. Where the library owns multiple copies of a popular book, the book_ID of that particular book will appear multiple times in the copy table. You can also specify that whenever you add a row to the copy table, the book_ID you use must already exist in the book table. Similar to primary keys, you can create a foreign key when you create the table by using the constraint_name foreign key clause of the create table statement. In the parenthesis for the foreign key clause, state the name of the column or columns that will be the foreign key, and then reference the table and primary key column that the foreign key links to. You can also use the rule clause to define what action to take if a row in the parent table, that is, the table with the primary key, is updated or deleted. For updates and deletes, you can specify to take no action, in which case the update or delete operation on the parent table may fail. For deletions, you can also specify to cascade the delete, that is, to delete the related child rows in the dependent table, or to set the values in the foreign key column of the child table to null. In this video, you learned that you can use primary keys to enforce uniqueness of rows in a table. Foreign keys are columns in a table which contain the same information as the primary key in another table. And you can use primary and foreign keys to create relationships between tables. Welcome to Indexes. After watching this video, you will be able to describe indexes, create indexes, and explain the advantages and disadvantages of using indexes. Usually when you add data to a table, it is appended to the end of the table. However, there is no guarantee of this, and there is no inherent order to the data. So when you select a particular row from a table, the processor must check each row in turn until it finds the one that you want. On a large table, this can become a very slow way of locating a row. Also, when you select multiple rows, unless you specify a sort order in your select statement, they may be returned in an unordered state. Because you often want to return the rows in a particular order or select a subset of sequential rows, you can create an index on a table to easily locate the specific row or set of rows you require. An index works by storing pointers to each row in the table. So when you request a particular row, the SQL processor can use the index to quickly locate the row. This is similar to how you use the index in a book to quickly find a particular section of the book. The index is ordered by values within the unique key upon which it is based. By default, when you create a primary key on a table, an index is automatically created on that key, but you can also create your own indexes on regularly searched columns. Use the create index statement to define the index, specifying the index name, its uniqueness, and the table and column on which to base it. Indexes provide the database user with many benefits, including improved performance of select queries when searching on an indexed column. Because the index provides a quick route to locate rows matching the search term, the results are returned quicker than when it has to check every row in the table. Reduced need to sort data. If you regularly require rows in a specific order, using an index can eliminate the need for sorting the rows after they are located. And guaranteed uniqueness of rows. If you use the unique clause when you create the index, you can be sure that updates and insertions will not create duplicate entries in that column while not bearing the overhead of having to check this against each row in the table. However, indexes do have a few disadvantages. Each index that you create uses disk space, in the same way that adding indexes increases the number of pages in a book, and decreased performance of insert, update, and delete queries. Because the rows in an indexed table are sorted according to the index, adding or removing rows can take longer than in a non-indexed table. You should only create an index when you will gain more from the advantages than you lose from the disadvantages. For example, on a table that rarely has rows inserted or updated, but is regularly used in select queries and where clauses. If you create many indexes on a table, you can actually negate the performance benefits in the same way that indexing every word in a book would result in an unhelpful index. In this video, you learned that indexes provide ordered pointers to rows in tables. Indexes can improve performance of select queries. And indexes can decrease the performance of insert, update, and delete queries. Welcome to normalization. After watching this video, you will be able to explain the purpose of normalization, describe first normal form, describe second normal form, and describe third normal form. When you keep records of data, such as books, in a bookshop, you will inevitably have some inconsistencies and duplicate information. Such duplication can cause extra work and inconsistencies if the data is updated because you must change it in more than one place. Normalization is the process of organizing your data to reduce redundant data, often by dividing larger tables into multiple related tables. Normalization helps speed up transactions because you perform updates, additions, and deletes only once on the normalized database. It also improves data integrity because it reduces the chance of a change being made in one place but not in another. As you begin the normalization process, it's important to recognize that you focus on normalizing each table until you reach the required normal form level. Normalization usually results in creating more tables, and once all the tables are normalized, you will have a normalized database. There are several forms of normalization, and most data engineers will need to be familiar with first normal form, second normal form, and third normal form. For a table to be in first normal form, each row must be unique, and each cell must contain only a single value. First normal form is also called 1NF. Let's look at how you would normalize a simple table. In this example, the book table contains some basic information about books, including title, formats, and authors. To meet first normal form requirements, each cell must contain a single value, not a list. In this example, you can see that all formats of a book are listed in the same cell. To normalize this table, you can add an extra row and split the two formats of patterns of software into their own row. So now you have a row for the paperback version and a row for the hardback version. Each cell in the table now has only one entry, and so the table is in first normal form. To be in second normal form, the database must already be in first normal form. Second normal form specifies that you should separate groups of values that apply to multiple rows by creating new tables. Second normal form is also referred to as 2NF. For clarity, this example shows just a subset of the data in the book table. Book 401 comes in both paperback and hardback format. So in the current form, it must be listed twice, once for each format. In this case, the format column contains values that apply to both rows that reference Book 401, and so there is some data duplication. To meet the requirements for second normal form and achieve just one row for Book 401, you can split the book table, so that the format information for the book is separated from unrelated information, such as title and author. Each resulting table is in 1NF. To maintain a relationship between the two tables, identify a primary key for one table that will be used as a foreign key in the other. In our example, the book_ID is unique to each book, so you can make that the primary key in the book table and include it as a foreign key in the format table. Now you can use it to link between the two tables to find the different formats of each of the unique books. To meet the requirements for third normal form, the database must already be in first and second normal form. Next, you must eliminate any columns that do not depend on the key. Third normal form is also referred to as 3NF. Let's consider some additional data about books, the publisher, and where the book ships from. Each publisher ships books from warehouses in their own location, so where the book ships from depends on the publisher, not the book ID. Therefore, the book table is not in 3NF, because the ships from data does not depend on the primary key. To meet the requirements of 3NF, you must separate the publisher and ships from information into a publishers table. Both tables are now in third normal form, which is as far as most relational databases go. There are also higher normal forms, such as Boyce-Codd normal form, or BCNF, which is an extension to the third normal form, as well as fourth and fifth normal forms, which may be needed for specific scenarios. In transactional systems, OLTP, where data is both read and written frequently, you typically normalize the data to 3NF. OLTP systems need to efficiently process and store transactions, as well as query transactional data. And normalizing the data to 3NF helps the database to efficiently process and store individual transactions. In analytical systems, OLAP, where the usage is mostly read-only, databases are optimized for read performance rather than write integrity. And hence, the data may have undergone some denormalization to a lower normal form before being loaded into the analytical system, such as a data warehouse. In data warehousing, data engineers are focused on performance, which can benefit from having fewer tables to process. In this video, you learned that normalization reduces redundancy and increases consistency of data. In first normal form, or 1NF, each row must be unique and each cell must contain only a single item. In second normal form, or 2NF, you must create separate tables for sets of values that apply to multiple records. And in third normal form, or 3NF, eliminate any columns that do not depend on the key. Welcome to Relational Model Constraints. After watching this video, you will be able to describe the different types of relational model constraints. Within any business, data must often adhere to certain restrictions or rules. Constraints help implement the business rules. In a relational data model, data integrity can be achieved using integrity rules or constraints. The following 6 constraints are defined in a relational database model: entity integrity constraint, referential integrity constraint, semantic integrity constraint, domain constraint, null constraint, and check constraint. To identify each tuple in a relation, the relation must have a primary key. The primary key is a unique value that identifies each tuple, or row, in a table. This is the entity integrity constraint. The terms primary key constraint or unique constraint are also used. This constraint prevents duplicate values in a table. To implement these constraints, indexes are used. The entity integrity constraint states that no attribute participating in the primary key of a relation is allowed to accept null values. The value null indicates that the value is unknown. In the entity integrity constraint, the primary key cannot have an unknown value. For example, in the relation author, author_ID is the primary key. The primary key identifies each tuple in the relation. The author_ID A1 points to author Raoul Chong from Toronto. If you replace the value A1 with null, you can still identify the author as Raoul Chong. However, if you also replace author_ID A4 with null, now you do not know which null value identifies which tuple. With the entity integrity constraint, no attribute participating in the primary key is allowed to accept null values. Referential integrity constraint defines relationships between tables and ensures that these relationships remain valid. The validity of the data is enforced using a combination of primary keys and foreign keys. As mentioned previously, for a book to exist, it has to be written by at least one author. The semantic integrity constraint refers to the correctness of the meaning of the data. For example, in the relation author, if the attribute or column city contains a garbage value instead of Toronto, the garbage value does not have any meaning. The semantic integrity constraint is related to the correctness of the data. A domain constraint specifies the permissible values for a given attribute. For example, in the relation author, the attribute country must contain a two-letter country code, such as CA for Canada or IN for India. If a number value of 34 is entered for the country attribute instead of a two-letter country code, the value 34 does not have any meaning. As you saw previously, the entity integrity constraint states that no attribute participating in the primary key is allowed to accept null values. The null constraint specifies that attribute values cannot be null. For example, in the relation author, if either last name or first name contains a null value, it could be difficult to identify the correct author. In this example, first name and last name attribute values cannot be null. An author must have a name. And finally, the check constraint enforces domain integrity by limiting the values that are accepted by an attribute. In the relation book, the attribute year is the year in which a particular book is published. If this were still the year 2010, it would not be meaningful to have a year greater than the current year. The check constraint would enforce the domain integrity by limiting the values that are accepted by the attribute year. In this video, you learned that the entity integrity constraint ensures the primary key is a unique value that identifies each tuple, or row. The referential integrity constraint defines relationships between tables. The semantic integrity constraint refers to the correctness of the meaning of the data. The domain constraint specifies the permissible values for a given attribute. The null constraint specifies that attribute values cannot be null. And the check constraint limits the values that are accepted by an attribute. Welcome to Getting Started with MySQL. After watching this video, you will be able to explain the ways you can use MySQL and describe some of the popular MySQL tools. MySQL is a popular open-source relational database management system, or RDBMS. MariaDB is a fork of the MySQL database by some of the original developers of MySQL. It's available in a range of ways to suit your needs. You can download and install the free Community Edition under GNU General Public License, and you can embed this in your own applications. Alternatively, you can purchase, download, and install commercial editions, such as Standard, Enterprise, and Cluster versions, which include additional functionality. MySQL is also available in the cloud. You can self-manage in virtual machine images or containers, or you can use a managed service such as IBM Cloud, Amazon RDS for MySQL, Azure Database for MySQL, or Google Cloud SQL for MySQL. There is a range of tools that you can use to work with your databases, including the MySQL command line interface, the MySQL admin command line program for administering your RDBMS along with other MySQL utilities for specific tasks, the MySQL Workbench desktop application for Windows, Linux, and Mac OS versions of MySQL, and the popular third-party web interface PHP-MyAdmin. The MySQL command line interface enables you to issue commands to interact with your MySQL server and data. These commands can be typed directly at the prompt for interactive use or from a text file that you invoke from the command prompt. This screenshot shows running the Show Databases command interactively to list the databases currently available. When running in batch mode, you can specify a file to store any output messages for later use. MySQL Workbench is a visual database design tool that integrates SQL development, administration, database design, creation, and maintenance into a single development environment for the MySQL database system. From the administration page, you can view connection details and server features as well as performing administration tasks such as importing and exporting data and reviewing server logs and performance reports. The Schemas page enables you to access the objects in your database, work with your data, and it provides direct access to the help documentation. PHP-MyAdmin is a graphical web interface that you can use to interact with your MySQL databases. When you first connect to the server, you see the server information and the system databases. You can then create your own user databases and use the different tabs to interact with them. You can create databases and tables, load and query data, and import and export data using PHP-MyAdmin. In this video, you learned that you can download and install MySQL on your own desktop and the servers. You can self-manage or use managed services for MySQL in the cloud. MySQL and MySQL Admin are command line interfaces for database management. MySQL Workbench is a desktop application for designing, developing, and administering MySQL databases. And PHP-MyAdmin is a web interface for working with MySQL databases. Welcome to creating databases and tables in MySQL. After watching this video, you will be able to create a database and table at the command line, create a database using PHP-MyAdmin, create a table, define columns, and edit the table definition. As with many RDBMS, you can create databases and tables in MySQL by using a command line interface, a graphical user interface, or API calls. In this video, you will see how to perform these tasks using the command line and the PHP-MyAdmin user interface. You will see how to create the database, then the table, and then how to define and edit the columns in that table. You can issue commands at the MySQL command line to create database objects. Use the Create Database command to create the database and create table for tables, specifying column names and data types. You can use the Describe command to show the structure of the newly created table. Alternatively, you can use PHP-MyAdmin to create the same database and table. PHP-MyAdmin is a popular visual tool with a web interface for working with MySQL. To create the database, in the tree view in the left-hand pane, click New. On the Databases tab, enter the name for the new database. Optionally, select the encoding for the data, and then click Create. This creates the database, which now shows in the database tree view on the left-hand side of the window and opens the Create Table tab. To create a table, enter the name of the table, in this case, employee_details, select the number of columns for the table, 4, and then click Go. In the next step, you define the columns for your table. Enter the name, select the data type, enter a length if relevant to that data type, and then click Save. You're then shown a summary of the structure of the new table in your database. Here, you can edit columns, drop columns, move them, or normalize the table. You can also add more columns if required. In this video, you learned that you can use a command line interface, a graphical user interface, or API calls to create databases and tables in MySQL. PHP-MyAdmin provides an easy-to-use interface to create databases, tables, and columns. And you can add and modify columns after you create a table. Welcome to populating MySQL databases and tables. After watching this video, you will be able to describe MySQL backup and restore functionality, explain how to load small and large amounts of data into MySQL, and describe how to export MySQL data to a CSV file. As a data engineer or database administrator, you will often need to populate databases and tables. One method of doing this is to back up an existing database containing your data and restore it to your new destination. You can use MySQL dump to back up a database to a .sql file containing all of the statements needed to recreate the contents of the database. The simplest use of this is shown here. The -u parameter specifies the username of root. Employees is the name of the database, and employee backup.sql is the name of the file in which to create the backup. If you want to just back up specific tables, you can list their names after the name of the database. And to restore a backed up file, you can use MySQL in a similar fashion. This runs all the SQL statements in the backup file to recreate the objects and restore the data in the destination database. Note that the greater than sign signifies output to the .sql file or backup, and the less than sign signifies input to the database or restore. If you're already at the MySQL command prompt, you can restore a dump file by using the source command with the name of the dump file. This method can also be used to execute SQL scripts from file. You can also back up databases using PHP-MyAdmin. Select a database in the tree view. Then, on the Export tab, click Go. By default, this quick export method generates an SQL file that contains all the script necessary to completely recreate the contents of your database. You can then use the Import tab to restore this database to this or another instance of MySQL. Select your destination database, locate the backup file, and then click Go. Again, this runs all the SQL statements in the backup file to recreate the objects and restore the data in the destination database. Alternatively, if you only want to populate a small number of rows in an individual table instead of populating an entire database, you can use the PHP-MyAdmin tool to manually enter rows or run SQL insert statements. To manually enter rows in PHP-MyAdmin, on the Insert tab, enter the data, then click Go. By default, you can enter 2 rows at a time, but you can increase or decrease this as required. And after you have entered data into a table, you can view that data on the Browse tab. Manually entering rows and running individual SQL statements is fine for small amounts of data, but if you're loading a large number of rows, you will find the import functionality is easier and quicker to use. You can use the MySQL load data in file statement to import the contents of a CSV file into an existing MySQL table, or you can use the MySQL import utility passing the name of the database that the table resides in and the name of the CSV file. The table name is inferred from the name of the CSV file, so you must ensure that your file name matches your table name exactly. Alternatively, PHP-MyAdmin provides a visual interface for importing data into tables. On the Import tab, click Browse to select your file. Check that the format and options have been correctly determined from the data file, and click Go. Using this method, you can import up to 2 megabytes of data at a time. You can also use PHP-MyAdmin to export data from a table to CSV format. On the Export tab, change the format to CSV, optionally specify which rows to export, and then click Go. In this video, you learned that you can use backup and restore functionality at the command line and in PHP-MyAdmin to populate databases. You can manually insert small amounts of data using PHP-MyAdmin. And you can use import and export functionality at the command line and in PHP-MyAdmin to populate tables and save their data to files. Welcome to using keys and constraints in MySQL. After watching this video, you will be able to create keys and use constraints. Similarly to other relational databases, MySQL supports keys and constraints, including primary keys, foreign keys, unique constraints, and null constraints. You can create these constraints either when creating your table or at a later time. In this video, you will see how to create and use keys and constraints in PHP-MyAdmin web interface, a popular visual tool for interacting with MySQL. You can create a primary key on one column or a combination of columns. Primary key columns cannot contain nulls, and the key definition enforces uniqueness on the column or combination of columns in the key. Creating a primary key automatically creates an index on the column or columns that make up the primary key. To create a primary key on a column when creating a table in PHP-MyAdmin, add an index of type primary and then confirm this by clicking Go. If you want to include another column in the key, just add a primary index to that column too. You'll then find a primary key icon next to the column name and an index named primary on the table. Often your table will have an existing column that fits the requirements of a primary key, such as the employee ID for the employees table. However, in other scenarios, you may want to automatically generate an ID number for each row as it's added to the table. The auto-increment property of a column enables this functionality, and, as with keys, can be set when you create the table or at a later time. On the Create table or the Structure tab, select the A_I checkbox for your primary key row and then click Save. Now, when you add data to the table, the database engine automatically generates incrementing entries for the employee ID column. You can also create foreign keys to relate data across tables. For example, you can use the employee ID column in the employee_details table to link to the employee ID column in the employee_contact_info table by creating a foreign key. To create a foreign key, on the Relation view of the Structure tab, enter the name of your key and identify the columns that define it. You can also specify what action to take when a related row is deleted or updated. And as with primary keys, the underlying index now also shows on the Structure tab. By default, when you create a MySQL table in PHP-MyAdmin, the columns are defined as not null. You can change this either when you create the table or by changing the column definition. For example, to enable null values to be entered in the start date and salary columns, select the Null checkbox. Leaving the employee ID, first name, and last name null checkboxes blank ensures that those columns require data. To ensure that the email address for each employee is unique, you can use the Unique constraint. On the Structure tab, click the More link for the relevant column, and then click Unique. In this video, you learned that you create primary keys by defining a primary index on one or more columns. You use auto-increment to automatically generate sequential numeric data in a column. When creating foreign keys, you can define onDelete and onUpdate actions. MySQL columns are not null by default, and you can configure a column to only accept unique values. Welcome to Getting Started with PostgreSQL. After watching this video, you will be able to describe PostgreSQL, explain how you can work with PostgreSQL databases, describe PSQL, and describe pgadmin, the query tool, and the ERD tool. Postgres is an open-source, object-relational database management system with a strong reputation for reliability and flexibility and support for both relational and non-relational data types. Postgres is a popular database choice for OLTP, data analytics, and geographic information systems. You can use PostgreSQL in a number of ways. You can download and install on your own servers on a range of operating systems such as Mac OS, Unix, or Windows. Or you can install and self-manage PostgreSQL in virtual machine images or containers in the cloud, or use managed services such as IBM Cloud Databases for PostgreSQL, Amazon RDS, Google Cloud SQL for PostgreSQL, Enterprise DB Cloud, or Microsoft Azure for PostgreSQL. There are a variety of tools that you can use to connect to PostgreSQL databases. PSQL provides a command line interface for PostgreSQL. pgadmin provides an open-source graphical interface to the database server, which is available as a desktop application or as a web application that you can install on your web servers. Navicat and dbeaver are commercial graphical interface options that you can use to access Postgres, MySQL, and other types of database. Managed database and cloud service providers are other options for working with PostgreSQL. For example, Amazon RDS for PostgreSQL provides a web-based management console and RDS APIs. PSQL is an interactive command line tool that you can use to work with your Postgres databases. You can run interactive queries and display information about the objects in your database. The screenshot here shows the library and Postgres user databases, and the internal Template 0 and Template 1 databases, which Postgres uses as templates when you create a new database. You can also use pgadmin to interact with your PostgreSQL databases. When you first connect to the server, you will connect to the default Postgres database. After you have created other databases, you can specify to connect directly to them. You can use pgadmin to complete all your development and administrative tasks, including creating databases and tables, loading data, querying data, writing stored procedures and functions, managing database objects, managing security, and monitoring usage. pgadmin includes the query tool that you can use to run SQL commands and view or interact with their results. In the upper pane, you can type or paste SQL queries, and the results are shown below. If the results are editable, you can use this area to edit the dataset. You can also use the tabs to see an explanation of the query plan, server messages, and asynchronous server notifications in this lower pane. PGAdmin also includes an ERD tool that you can use to create an ERD for an existing database, or to create a new ERD and generate the SQL statements for creating the underlying database objects. To create an entity relationship diagram from an existing database, right-click the database and then click Generate ERD. The tool reviews your database structure and generates a visual diagram of the tables in the database and the relationships between them. You can reorganize the tables, add, edit, and delete relationships, add notes, and generate SQL statements in the tool. In this video, you learned that you can install PostgreSQL on your own servers or work with it in the cloud. PSQL provides a command line interface to a Postgres server, and PGAdmin is a popular database management tool for PostgreSQL, which includes object navigation, the query tool, and the ERD tool. Welcome to creating databases and loading data into PostgreSQL. After watching this video, you will be able to create databases and tables at the command line and using PGAdmin, backup and restore databases, and import data to and export data from tables. As with many RDBMS, you can create databases and tables and load data into Postgres by using a command line interface, a graphical user interface, or API calls. In this video, you will see how to perform these tasks using the PSQL command line interface and the PGAdmin graphical user interface. You will see how to create the database, then the table, and how to define and edit the columns in that table. Then you'll see how to load data into your database. You can use PSQL to issue commands to create and interact with database objects and data. Use the Create Database command to create the database, and Create Table for tables, specifying column names and data types. You can use the \d command to show the structure of the newly created table. And after you've created the database, you'll likely want to load data into it. At the command line, you can use PSQL to restore a database that was previously backed up using pg_dump. Just specify the name of the destination database and the name of the dump file. This will recreate the tables and any other database objects, as well as the data that was present when the dump file was created. Alternatively, you can use PGAdmin to create the same database. PGAdmin is a web-based visual tool you can use to work with Postgres. To create the database, in the tree view in the left-hand pane, right-click Databases, click Create, and then click Database. Enter the name for the new database, and then click Save. If you want to restore the whole database from a dump file, select the database that you want to restore to in the tree view. Click Restore, and then in the Restore box, enter the location of your dump file. This runs the SQL statements contained in that file to recreate the database objects and data in the current database. Alternatively, you can manually create tables using PGAdmin. In the tree view, right-click Tables, click Create, and then click Table. On the General page, enter the name for your table, in this case, employee_details. And then on the Columns tab, enter the details for your columns and click Save. You'll then see your table and columns in the Tables section of the Tree View pane. From here, you can use the Import-Export function to load data into your new table. In the Import-Export data box, select Import, then enter the location and file name for your data file. If you're loading data from a CSV file, you do not need to specify the delimiter because it's the default option for CSV files. You can then use the View Edit Data option to review the loaded data. This runs an SQL query to display the data in the selected table. You can also use the import-export function to export existing data in your database to a CSV file for use elsewhere. CSV is the default format, so you can just specify the file name and click OK. If you want to back up the entire database, you can use the pg_dump utility. The syntax of this is similar to restoring data using PSQL. Specify the database name and the file name for the dump file. By default, pg_dump creates an SQL file containing a script that describes all the objects and data in the database. You can also customize the command to output to a compressed archive file instead. By default, pg_dump backs up the entire schema and data in the database. In this video, you learned that you can use many tools to create Postgres objects, including the PSQL command line utility and pgadmin. You can use pg_dump to back up databases, and PSQL to restore them. And finally, you can use the pgadmin import-export tool to load data into and export data from tables. Welcome to Views. After watching this video, you will be able to describe views, create and use a view, explain how materialized views differ from regular views, and create and use a materialized view. A view is an alternative way of representing data from one or more tables or other views. You can interact with views in the same way as you interact with tables, inserting, updating, and deleting data as required. Views are a useful way of limiting access to sensitive data, simplifying data retrieval, and reducing access to underlying tables. For example, you could create a view to include the name and the email columns from these two tables. Users can then easily access this data without needing to know that it is stored in two different tables and without being given access to the sensitive salary information. In pgadmin, you create views within a schema. So, in the tree view on the left-hand side, right-click Views, click Create, and then click View. This opens the Create View box in which you first need to name the view. And then on the code page, you enter the SQL code that defines the view and then click Save. You'll then see your view in the Views folder, and you can expand the view to display the columns included in it. To run the view, right-click the view name, click View Edit Data, and then click All Rows. You will then see all the rows included in the view. PostgreSQL also supports another type of view, a materialized view. When you refresh a materialized view for the first time, the result set is materialized or saved for future use. This materialization does mean that you can only query the data and cannot update or delete it. However, it also enhances performance for future querying of the view because the result set is readily available, often stored in memory. Creating a materialized view is a similar process to creating a regular view, but you must ensure that you start in the materialized views folder in the tree view. After entering the name for the view on the definition page, enter the code to define the view. This example includes just the employee ID and salary columns from the employee_details table to anonymize the salary information. Then click Save, and the materialized view is added to the folder. Because the view stores the data, before using it, you need to refresh it with the current rows. And then you can use the view to access the data it holds. You can refresh the data in the view at any time to update it with the data in the underlying tables. In this video, you learned that views are an alternative way of representing data. You can use views to limit access to sensitive data and simplify data retrieval. Materialized views store the result set for quicker subsequent access. and you cannot insert, update, or delete rows via a materialized view. Welcome to Approach to Database Design. After watching this video, you will be able to describe the importance of good database design, explain the database design process, and describe the purpose of an ERD tool. A well-designed database is crucial to the success of any data-driven project. The design of the database contributes to the integrity of data, the reduction of redundant data, application performance, and user satisfaction, which are all key markers of a successful project. As such, it is essential that you spend the time upfront designing your database to avoid costly problems at a later date. There are 3 key steps in the database design process. Requirements analysis, where you analyze the data you are working with and the requirements for the use of that data. Logical design, where you plan how to organize your data. And physical design, where you plan how to implement your logical design in the database management system you will be using. During the first stage, you gather and analyze real-world business information and policies. You need to identify the base objects in the data and the relationships between these objects. For example, in a library scenario, person borrows a book. You also need to identify the information associated with these objects that you will use to interact with them. For a book, this could be the title, description, ISBN, and authors. And for a person, it could be their name, address, and contact details. How you obtain this information can vary from project to project, but is likely to include reviewing any existing stores of this data, be that in a database, other electronic format, or even a paper-based system. Interviewing users to determine how the business currently uses this data. And interviewing users and potential users to determine how the business could make better use of this data. If the data currently resides in a database, when reviewing the existing structure, be sure to use it as a source of information about the data, rather than a starting template for your own database design. The output from your requirements analysis could be a report, a data diagram, or a presentation that you can share with stakeholders to validate your understanding of the system. In the logical design phase, you take the requirements you identified in the analysis stage and map them to entities, attributes, and relationships. However, logical models should not specify any technical requirements, so you should not be thinking about any implementation considerations at this stage. The objects that you identified in the previous stage become entities. Generally, entities are people, events, locations, or things, and if you find you have an object that doesn't fit into one of these categories, you should double-check that it really is an object rather than a characteristic of another object. The characteristics of the objects will become attributes. So, the book object becomes a book entity, and the person object becomes a person entity. At this stage, you should also try to think about the attributes of your entities. You may think of a person having a name, but in database terms, it is better to think of them having a first name and a last name. This makes it easier to search on and sort by either first or last name. And although the requirements analysis identified that a person has an address, when you think about storing that address, you should divide it up into its constituent parts. When analyzing the requirements, you identified that a person borrows a book. However, a person may borrow many books, and a book may be borrowed by many people. So this is a many-to-many relationship, which can lead to ambiguity in a database. The easiest way to solve this is by creating 2 separate one-to-many relationships by introducing an associative entity in between the existing ones. In the book-to-person scenario, you can add in a loan entity. One person can have many loans, and one book can be loaned many times. The loan entity will contain attributes from the book table and the person table, as well as some loan-specific ones. You could relate these entities by their matching attributes, however, none of those are guaranteed to be unique. In the book entity, the ISBN will be unique, so you could use that as the primary key. You could then use the ISBN instead of the book title in the loan entity to identify the borrowed book. There are no unique attributes in the person entity, so you can add an identifier attribute to that entity and use that to link the loan to the person. And you can add a loan ID to the loan entity to uniquely identify each loan. Now that you have your view of your entities and attributes, you can consider normalization. Most OLTP systems are normalized to the third normal form for optimal transactional performance, whereas OLAP systems are generally denormalized to enhance read performance. To adhere to first normal form, you need to remove the potential of two or more authors' names being listed in the author's attribute for an individual book. One option is to split this into Author 1 and Author 2 attributes. However, there's no guarantee of a maximum number of authors for a book, and this would not adhere to second normal form. So, a better way is to create a separate authors entity with a many-to-one relationship to the book entity. When you have finished normalizing your entities, you can move on to the physical design stage, how your database will actually look. At this stage, you can start to consider the impact that your choice of database management system will have on your design. For example, the data types it supports, the naming rules it implements, and the indexes and constraints it supports. When you are thinking about naming rules, you should also consider implementing your own convention so that anyone working with your data will understand your schema. So the person entity from your logical design will become a person table in your physical design, with each attribute becoming a typed column and keys being defined. You can use an ERD designer to create your entity relationship diagrams. PGAdmin includes the ERD tool in which you can design your ERD and then generate an SQL script that will create your database and objects based on your design. In this video, you learned that it is important to spend time designing your database before you start the implementation. There are 3 stages of database design: requirements analysis, logical design, and physical design. And using an ERD designer can simplify the design process.